This is going to be the last video for Chapter 11 that we're going to cover. Section 11.10, looking at molecular shape and the valence shell electron pair repulsion model, also known as VSEPR. So VSEPR is actually a theory that helps us predict the geometries of molecules based on their bonding and non-bonding electrons, also their electron pairs, and we're going to see that those electron pairs are actually the most important part in understanding how to predict geometries. So these are the four main ones we're going to talk about. There's one additional one we'll see as a later example, but you can sort of see these examples here looking at a sort of a stick model and a space filling model. So space filling shows how the action atoms are aligned in real life, and the bottom ones where we actually have a ball and stick, it just helps a little illustrate how the bond connections are made. So we'll start out with our V-shaped one. We're going to call this one bent. That's our water one. Carbon dioxide here is going to be known as linear. Boron trifluoride is trigonal planar, and our methane is tetrahedral. So our linear geometry is going to result when we have our two electron pairs or our two atoms surrounding one central atom. So here we have our formula beryllium chloride, where we have our two chlorines. They're going to separate on either side, showing a linear geometry. Our trigonal planar is going to be when we have one central atom surrounded by three electron pairs. Here we can see boron having three fluorines on the outside. All of them have 120 degrees between them. Our tetrahedral, we're still going to be dealing with our one central atom, but in this case we're going to have four electron pairs. So in our example of methane, we're going to see our H's all separated by 109.5 degrees, and what the flat picture on the right doesn't help you illustrate, but we have these all in different planes, so that's how they're able to space out. Now lone pairs are going to become important when we're predicting our shape. So let's look at ammonia, where we know we have our single nitrogen atom in the middle with our three hydrogen atoms, and in addition our lone pair. If you look at the figures on the bottom, looking at part B, we actually can see that our electron orbital that's holding these lone pairs is slightly bigger than our other hydrogens. So we end up having a little bit more space for those. So on the reverse side, where we saw our trigonal planar meaning all lying on the same plane, our pyramidal is going to look more like a pyramid shape, a cone. Now let's go back and look at our bent water molecule. We know that lone pairs actually shape geometry. So in this case, we're going to see our lone pairs sort of bend out towards one another, all right, leaving our hydrogens in the same plane and our electrons in another. This is going to give us our bent. So it's going to be similar to tetrahedral, but rather than having four atoms on the outside, we're only going to have two, and then two lone pairs. So these again are our five options: linear, trigonal planar, tetrahedral, pyramidal, and bent. It's pretty easy to distinguish between linear, planar, and tetrahedral. You're dealing with just this number of atoms. When you know you have lone pairs, you're going to classify those as pyramidal or bent. So in order to determine shape, you're going to try to draw the Lewis structure, count your electron pairs and arrange them, determine the position of the atoms based on number 2, and then provide the geometry. So let's look at this first example. What is the molecular geometry for formaldehyde? This one's going to be trigonal planar. Let's take a look why. We're going to see our Lewis structure having our central atom carbon. We'll have a double bonded oxygen with two hydrogens. In this case, even though our oxygen is double bonded, we're still going to have three atoms connected to our central atom, giving us our trigonal planar option. In this case, we're looking at phosphorus trihydrogen, phosphide. So let's take a look at our options here. This one's going to be trigonal pyramidal because we have our extra lone pair on the top of our phosphorus. So in this case, we would need to have that electron pair giving us our specific shape. So this would look very similar to a tetrahedral, but since that our fourth connection is not a hydrogen, it's a lone pair, we're going to classify this as trigonal pyramidal.